Okay, good afternoon, everyone. I guess my talk today is going to be on, while I'm writing this long title, I'll explain sort of what I'm going to go through. So it's called Sumcheck Protocol over Fields of Small Characteristics. So there's three algorithms presented in the paper. I'm only going to go through algorithms 1 and 3. First, I'll start off with a bit of the motivation of why they came up with a new algorithm, and then I'm gonna sort of share the results that they presented in the paper. Yeah, so that's sort of like the run through of what I'm gonna go through. Right. So I guess before I begin, does everyone have like a rough idea of how Sumcheck works? So if you don't know how Sumcheck works, raise your hand. Okay, then I guess I don't, maybe I don't have to go through. Okay, sorry? Okay, I'll do like a quick speed run of how Sumcheck works. Right, so basically, in Sumcheck, usually what we have is like a multilinear polynomial. Let's call it gx, and when I'm saying multilinear polynomial, I mean like you have, say, multiple variables, right? Let's say it's an L-variate polynomial. So you're gonna have like, let's say x1, x2 plus, let's say x3, then plus like x1, x4, da 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 da, right?
So x is directed here.
Sorry?
X is directed here. Gx, x is directed.
So, yeah, you can see it that way, right? So it's just variables in the multivariate polynomial, multilinear polynomial in this case, because yeah. So then the goal.
Left the x is a vector about x1, x2, x4, right? The equation left gx, the x is.
Yeah, you can see it that way, I guess. Depends on how you represent it, right? Yeah, because then this is like it can be like yeah, x1, x2, and then if we have an L variate polynomial, it means like we have until xl, right? And then if we plug in all the values, we solve the polynomial. So usually the goal of Sumcheck is to solve to sum this up over a Boolean hypercube, which is just essentially that the variables can take 0 and 1. And I'll just briefly talk about the protocol itself. So it's an interactive protocol, which means that, sorry, yeah. Oh, okay. Yeah, so in round 0, so let's say round 0, what you do is the prover sends a claim C to the verifier. And then, yeah, so that's sort of round 0. And then round 1, the prover also sends a univariate polynomial of claim to be equal to some h1 of x, where h1 is basically the multilinear polynomial that you have here, but you leave the first variable free. So it looks something like, so it'd be something like, say this one is equals to, so it'd be like x. So here we have x1 because, or rather, let's say x2, right? Because we leave the first variable free, and then until xl. And then this is like gx. So this is the free variable. And then we have like x2, da da da, all the way until xl. So what the prover sends is some polynomial s1 that claims to equal this, right? And then in the next round, say here, the verifier checks that, because the verifier has the claim now, and because the prover also sends this univariate polynomial, the verifier can check that C equals to S1, 0 plus S1 of 1. right? Because here we kind of know that the first variable is free, so we just plug in the values and then we can check the claim that way. Then now the verifier also wants to check that the S1 of x, the free variable, is equals to H1 of x. But then here, this is where we pick, the verifier picks like a random value from the field. So let's say, let me write up here maybe. So the verifier samples R from the field and then computes S1, R1. R1 just means that it's the random variable for the first free variable. But then if you want to check like H1, R1, right? You can't easily do this because essentially that's computing the original problem. So you sort of recursively do some check on this. So then you would have to do this for L rounds to get all the way until here, right? So this is the final round that you have to do. And then in the final round, the verifier has to evaluate this a single time to sort of check that it's correctly computed. Yeah, so by the end of this protocol, what the verifier is kind of evaluating is kind of like a bunch of just random variables, right? And then you have all the way until RL. And all these are sampled from the field. So that's roughly a speed run of Sumcheck. Yeah, any questions? Yeah.
The R's, are they also in the Boolean hypercube?
They're from the field, so like whatever base field you choose. Yeah.
Field.
Yeah.
Okay.
So yeah, maybe now let's talk about the paper itself. So the paper presents two algorithms. One is the original algorithm, and the second one is the sort of improvement. And maybe I'll give a bit of motivation for why they came up with this new algorithm. And basically, sort of the key finding they had was because notice when we sample from the random, we sample the random variable, right? We have to do extension field operations basically. And that kind of means that we have to do sort of, they're basically more expensive than base field operations. And the background, or rather the findings of recent papers like Benius found that, small field is good, right? Small field is very good. So that's one. And the second thing is like, with Benius, you have like faster hashing-based commitments and Sumcheck IOP. And that could mean that Sumcheck itself could be the bottleneck, right? And the key improvement of this new algorithm over the original algorithm is that they basically replaced the extension field multiplications with more base field multiplications, basically. So I'll present a bit later on about what that exactly means, but basically, past a certain number of rounds, you're doing more base field multiplications. But past a certain number of rounds, these trade-off isn't worth it anymore. So what they are proposing is use this new algorithm up to a certain point and then switch back to the old algorithm.
Isn't it less secure to use a smaller field though? Because Benius uses towers, right?
Yeah.
So how do they define security over a smaller field?
So yeah, maybe I'll go through that a little bit later, because what they do is essentially, and this is the crux of the optimization. So all they are doing is viewing the extension field elements as a linear combination of the base field elements. Yeah. So Okay, so I'll quickly go through the algorithms, I guess. So I'll just write here algo 1. And I guess I have some maybe some key definitions here to share. So in the paper itself, they have some key terms called like BB, BE, and EE. So essentially, this just means like base times base, base times extension, and extension times extension. So they measure the costs based on this metric. I wouldn't use them now, but I'll use them a bit later. So I'll sort of go through algorithm 1, round 1 and round 2, and then generalize over round I, and I'll do the same for algo 3. And I'll skip over algo 2 because it's a bit like I can show my point just with the 2 algorithms that I'm going to present. Yeah, so with algo 1, round 1, what we are calculating is S1 of 0 and S1 of 1, and also S1 of 2. Oh, and this is, of course, like assuming the problem we want to solve here is actually a sum of, let's say, 2 polynomials. So Px multiplied by Qx. So this is the sum check that we want to solve. So then the degree would be 2 here. Or rather, yeah, the d is 2. And we're going to have 3 roots. That's why we're doing 1, 2, and 3. And then if we want to solve this, basically what we do is we have summation of x in 0, 1, L minus 1, P0x. Remember the point about leaving the first variable free. So here we're doing the same thing. And also here, sorry, this is comma. Yeah. And sort of we do a similar thing for S1 of 2, but we calculate it based on the lemma, which basically allows us to sort of reinterpret polynomial as something like, say, 1 minus 2 p plus 2 okay, and then dot again 1 minus 2, and then q plus 2q1. Yeah, so we can sort of re-express it something like this. So
just to confirm, P and Q are univariate polynomials of degree 2?
Yeah. So that's the, yeah.
Okay.
And that's the sum check that we're trying to solve. Yeah. How much more time do I have?
No more.
No more time. Okay, yeah. Okay. I'll finish very quickly. So I guess the key finding here is that when say in algorithm 3, I'll skip to algorithm 3 maybe. It's a bit, but basically this costs in terms of E in algo 1. This is about n over 2 I minus E multiplications. So then, yeah. So, yeah. And then in algo 1, what they do here is they actually store this in like 2 vectors, so A and B, A and B. But in Algo 3, all they're doing is, so they store all evaluations of like P and X here. So all they're doing differently in Algo 3 is they store, instead of storing them separately, they store it all in C, in the vector C. And this is the evaluations of Px dot Qx. And they use the observation that there's a certain, when they're calculating this S1 of 2, okay, maybe just to wrap up, they they found that there's two terms that they multiply inside while calculating this. That's actually calculated before. So they sort of re-express the terms in terms of base field multiplications. And then the cost ends up being something like, to calculate this ends up being something like 2n. And on round I guess, the cost is actually around at 2n I minus 1 times n base field multiplications. So this is the cost profile of the optimization, and this is the original cost, sort of. I mean, with a bit more detail, but basically, when you switch from Algo 1 to 3, you're doing more base multiplications, and in Algo 1, you're doing like extension multiplications. And basically, I'll just share quickly the cost profile of the Algo 3. So what they found was that when they're using Algo 3, for extension degree 4, right? Because for Binius and other similar small fields algorithms, you're doing extensions for the challenges. The improvement over Algo 1 for Algo 3 is actually 1.3x faster. But for, let's say if you want to extend to 1 to 8 degrees, it's actually like 10x faster. And the switchover, they also calculate like the optimal switchover rounds. And they found that for degree 4, you do Algo 3 until round 4. So when round 4, you switch from Algo 3 to 1. And then for the extension degree of 1 to 8, you switch at round 7. And that's how you combine the two algorithms to get better Sumcheck performance, I guess. Yeah. So I had to skip over some details, so if you want to discuss. Yeah.
So I want to make sure how many people have it demo. One.